This video is brought to you by mywayteaching.com.
So in this part, let us study the few common forces that we use in mechanics. In mechanics, we encounter several kinds of forces, like the gravitational forces, of course, the one of the important force, isn't it? Every object on the earth experiences the force of gravity due to the earth, and gravity also governs the motion of celestial bodies. The gravitational force can act at a distance without the need of any intervening medium. So, one of the basic forces, gravitational force exerted by the earth on all the objects. All the other forces common in mechanics are contact forces. Okay, this is one of the important force, that is contact forces. Okay, as the name suggests, a contact force on an object arises due to contact with some other object. It can be solid or fluid. See, when bodies are in contact, for example, a book resting on a table, a system of rigid bodies connected by rods, hinges, and other types of supports, there are mutual contact forces for each pair of bodies, satisfying the third law. The component of contact force normal to the surface in contact is called as normal reaction. Okay, the component of the contact force which is normal to the surface in contact. So if I say two bodies are in contact like this, the force which is normal to this, okay, the force which is normal to this is nothing but the normal force. We can represent it using R. The component which is parallel to the surfaces in contact is called as friction. So there is some frictional force between these two bodies, isn't it? That force is nothing but friction. And the contact forces arises also when solids are in contact with fluids. Solids are in contact with fluids. For example, a solid immersed in a fluid, you can see that here in the figure. Okay, the solid is immersed in a fluid. There is an upward buoyant force equal to the weight of the fluid displaced. So the viscous force, air resistance, etc. can also be the examples of contact forces. And two other common forces are tension in a string and the other force due to spring. When spring is compressed or extended by an external force, a restoring force is generated. As soon as you take out your finger from that spring, again it will be deformed or it will come down to its original shape, isn't it? That is called as a restoring force, and this force is usually proportional to the compression or elongation. So the spring force F is written as minus kx. Okay, we can write the spring force F as minus kx, where x is the displacement and k is the force constant. The negative sign denotes that the force is opposite to the displacement from the unstretched state. For an inextensible string, the force constant is very high. So the restoring force in a string is called as tension. It is customary to use a constant tension T throughout the string. This assumption is true for a string of negligible mass. Okay. We already learned in the first chapter that there are four fundamental forces in nature, isn't it? And of these, the weak and strong forces appear in domains that do not concern us here. So, only we are dealing with gravitational and electrical forces. So, we are dealing with those two here. So, the different contact forces of mechanics mentioned above fundamentally arise from electrical forces. They may seem surprising since we are talking of uncharged and non magnetic bodies in mechanics. At the microscopic level, all bodies are made up of charged constituents, and the various contact forces arising due to elasticity of bodies, molecular collisions, and impacts can ultimately be traced to the electrical forces between the charged constituents of different bodies. So, we are going to study about all these different contact forces. Okay, the detailed microscopic origin of all these forces is very much complex, and here we are not dealing with all those things. Okay, so this is some of the common forces in mechanics, especially the gravitational force and the contact force and the frictional force. So these are all the basic forces that we are dealing in mechanics. Okay, so now let us study about the important force, that is friction. Okay, so let us return to the example of a body of mass m at rest on a horizontal table. You just consider this example. See, the mass m of a body is at rest on a horizontal table. Now suppose a force F is applied horizontally to the body. You just see here, a force F is applied horizontally to this body. So we know that a small applied force may not be enough to move the body. But if the applied force F were the only external force on the body, it must move with an acceleration of F by m. If the force F, what we are applying, if it is the only external force, then it should move the body with an acceleration of F by m, because F is equal to ma. We know that, isn't it? However small, clearly the body remains at rest because some other force comes into play in the horizontal direction and opposes the applied force F, resulting in zero net force on the body. But here we are seeing that the body is at rest, it is not moving, which means that some other force in the opposite direction is acting on the body, and it is making the net external force which is acting on the body zero. Okay, so that force Fs, which is parallel to the surface of the body in contact with the table, is known as frictional force. So this opposing force is nothing but frictional force. Okay, or we can call it as friction. The subscript S stands for static friction to distinguish it from kinetic friction Fk, that we consider later. So note that static friction does not exist by itself. When there is no applied force, there is no static friction. Means if there is an applied force, then only we can expect this static friction. It comes into play the moment there is an applied force. As the applied force F increases, Fs also increases. Okay, if the applied force F increases, then the static force Fs, the static frictional force Fs also increases, remaining equal and opposite to the applied force F. So, keeping the body at rest. Hence, it is called static friction. Static friction opposes the impending motion. The term impending motion means that the motion that would take place under the applied force if friction were absent. So we know from this experience that as the applied force exceeds certain limit, the body begins to move. So okay, up to some limit, this frictional force, that to the static frictional force, opposes the body, isn't it? But if the applied force, if you keep on increasing the applied force at one stage, we can move the body, isn't it? Is that possible? Yes, that is possible. So there is some limiting value for that frictional force above which if we apply the force, then we can easily move the body, isn't it? So that is called as Fs max. It is independent of the area of contact and varies with the normal force N. So we can write that force as Fs max, which is given by mu s into n. Okay, where mu s is a constant of proportionality which is depending only on the nature of the surfaces in contact. So this is constant of proportionality. Okay, the constant mu s is called coefficient of static friction. The law of static friction may thus be written as Fs is always less than or equal to mu s and into n. So this is the law of static friction. Okay, if the applied force exceeds this Fs max, the body begins to slide on the surface. It is found experimentally that when relative motion has started, the frictional force decreases from the static maximum value Fs max. So, frictional force that opposes that relative motion between the surfaces in contact is called as kinetic or sliding friction, which is denoted by Fk. So the frictional force which opposes this the sliding friction, or we can say the frictional force which opposes the movement between these two bodies in contact, that is called as kinetic friction, like static friction. So when the both the bodies are in motion, this kinetic friction comes into play. Okay, it is found to be independent of the area of contact. Further, it is nearly independent of the velocity. Again, it satisfies a law similar to that of static friction. So Fk is given by mu k into n. Okay, where mu k is the coefficient of kinetic friction. It depends on the surfaces in contact. So as mentioned above, experiments show that mu k is always less than mu s. The coefficient of this kinetic friction is always less than the coefficient of static friction. When relative motion has begun, the acceleration of the body according to the second law is, so once the motion has started, then the acceleration of the body will become F minus Fk by m. Okay, for a body moving with constant velocity, F is equal to Fk. If it is moving with constant velocity, if the applied force on the body is removed, its acceleration is minus Fk by m, and it is eventually come to stop. So the laws of friction given above do not have the status of fundamental laws like those for gravitation, electric and magnetic forces. These are all just empirical relations that are only approximately true, but they are very much useful in doing practical calculations. Okay, thus when two bodies are in contact, each experiences a contact force by the other, isn't it? And friction by definition is the component of contact force which is parallel to the surfaces in contact, which opposes impending or actual relative motion between the two surfaces. The role of friction force is that only it just opposes the motion between two bodies. It is not exactly, it is not motion, we can call it as relative motion that the frictional force opposes. Okay, it opposes the relative motion. You just consider a box lying in a compartment of a train that is accelerating. If the box is stationary relative to train, it is in fact accelerating along with the train, isn't it? The horizontal direction is the force of friction. Okay, the force which is in the horizontal direction is the force of friction if you can in that particular box case. If there is no friction, then the floor of the train would slip by and the box would remain at its initial position due to inertia. So this impending relative motion is opposed by the static friction Fs. So the static friction provides the same acceleration to the box as that of the train, keeping it stationary relative to the train. Okay.